this work is joint with Masaki Casedo and Maria Aparecida Ruas. And I'll talk about some parts of 2 works. Before this, I will give some preliminaries about the space-like surface in the de Sitter 5 space, the second fundamental forming, and the asymptotic direction that we consider here. The first paper was published in 2015, and it was about the geometry of some special intersection about a cone and a special ellipse that gives to us some invariants and the classification of the second fundamental form. Give also the number of asymptotic directions and the number of binormal directions in this case. And in the second paper, published in 2019, we give some properties and singularity related to the equations of these asymptotic directions and of these binormal directions. Then I will talk about some parts of these 2 works. And our goal here is to show that we found some related singular surfaces when we consider the equation of the asymptotic directions that I will explain after. This equation is a BDE. Here I call V a vector in the tangent plane of our space-like surface. Then you have the solutions here, at most 4 solutions for the asymptotic direction in this case. And when we consider this equation, and we think about this, the surface that is a lifting surface of these directions, given by FAD, minus 0, this gives you a non-singularity surface. But I just to comment here in the beginning that for the first time, we thought that this surface will have a no isolated singular surface. No isolated. Yes. At the first, we thought that we will find the surface with isolated singular has an isolated singular surface. Then we tried many times to prove that this kind of singularity was so degenerate. But in the end, we convinced that this was not no isolated, and we need to change the approach to prove that it was not an isolated singularity. And because it was a surprise for us, in this context, we don't know other cases where appears non-isolated singularity. Then, just to comment about the asymptotic directions, the asymptotic directions is studied for surface in R3, R4, and R5 in these 3 first papers by Little, Moshida, Romero Fuster, Ruas, and also Ronaldo Garcia around 2000. After by Romero Fuster, Ruas, and Tide study in 2008. And also by Martins, Nuno Ballesteros, but here for singularity surfaces in 2016, by Ossietzky, Benedini, and Ruas in 2018, also for non-isolated singularities, for singular surfaces. And it was also studied by Sanchis, Bringas, and by Arde. Here for Minkowski space, that also is our case. And in this paper appears then the curvature ellipse, the parabola ellipse, the hyperbolic, the curvature parabola, and the curvatura hyperbola. In our case, we are considered then space-like surface in the de Sitter 5 space. The Minkowski space is given, we call here Rn plus 1, 1. And it has this inner product that has a minus here, for example, in the first coordinate. Then we have vectors that x can be 0 without x be 0. And these vectors are in LCN that we call light cone. Okay? Then the light cone here in R3, just to have some idea. Inside the cone, xx is less than 0. Then we call the vectors by time-like vectors. Outside, xx is greater than 0. Then we call this by space-like vectors. This plane is an example of a space-like plane because of all the vectors are space-like in the plane. Then, when we consider embedding in the light cone, or in the de Sitter space, in the de Sitter 5 space, we have a space-like surface if at any point you have that the plane is a space-like plane. And the de Sitter space is given by a pseudosphere that is given by xx is equal to 1. Then if we represent this in R3, 1, then we have that the de Sitter space is given by these pictures. And here I draw only some curves in the 2 de Sitter space. But in fact, we will work with space-like surfaces in the 5 de Sitter space. Then, in our case, we have a normal space, 3 space, that we took here as 3 vectors, orthonormal sections. That is a base for our space. The first one is time-like, and the second and third one are space-like. We represent here by E a vector in the light cone. Then this vector here is a light-like normal. And the coordinates of this vector with respect to this base is 1 for the first vector, cosine theta, and sine theta for the other vectors. Then we will say that theta represents this light-like normal vector that we consider now. For the second fundamental form, then you know that you need to project the embedding the second order derivatives of the embedding with respect to the normal vectors N0, N1, and N2. Then you have AY, A0, A1, A2, B0, B1, B2, and A2, B2, C2. This is the second fundamental form related to the like normal, E, that is given by these coefficients. Then we call here L, the coefficient of du1, 2, and M and N. And we know here that L, M, and N is given by this formula, where we multiply the coefficients of the second fundamental form by the coordinates of the vectors that we are considering here, that is a like normal vector. And we call by alpha the transpose of this matrix. That is, we call the matrix of the second fundamental form. The first line here is a vector A, the second is a vector B, and the third one is a vector C. In the first paper, we explore more this because this defines a vector A that is a center of an ellipse, and a vector B and C that generates a plane. Here you have a special ellipse that we study the position of the ellipse with respect to a special cone to classify then the normal forms that I showed now in a few minutes. Okay? But there is some geometry that I will not explore here, but it's a beautiful interpretation also. Then, the asymptotic directions that we are considering is given by, we consider a V in the tangent space. It's asymptotic directions if and only if the second fundamental form at V is equal to 0 for some binomial direction theta that represents our like normal vector. And also we have here that equation that gives this binomial direction that you will not explore here, but there is an equation for the binomial direction also. And you use the fact that the asymptotic directions are invariant under the choice of the orthonormal sections and the coordinate chains on M. To classify, then, the second fundamental form given by the matrix 3 by 3, we consider the action of the group, the linear group that acts in the source of the embedding of the surface, and the Lorentzian group that acts in the normal sections of M. And we prove that the signs of the discriminant that gives the binomial directions and the rank of the matrix of the second fundamental form are invariant under these actions. Based on this, we classify all the normal forms for the matrix 3 by 3 of the second fundamental form given by alpha. When it has rank 1, rank 2, or rank 3. But here, I will just present the normal forms for rank 2, because this case is related to the singularities of this surface. Then, in this case, we have 5 normal forms with at most 3 parameters, bi, ci. And this is based in the we explain also in accordance with the position of the plane, that is a plane given by BC. If we compare this plane with a special cone that we call M2 hyperbolic, M2 parabolic, or M2 elliptic, if it cuts the cone or it's tangent the cone. And also in the first case, we need to consider some difference about the vector A, that is the center of the ellipse. Consider if this A is elliptic, parabolic, or hyperbolic, that is inside the cone or outside the cone or on the cone. Then we got, with that action that we are considering, we got these 5 homomorphisms. We prove that the equation of the asymptotic directions, we can write like this. Then there is at most 4 asymptotic directions passing through any non-inflection points and the non-conic points on a generic space-like surface in the de Sitter 5 spaces. This direction are solution of these binary differential equations. And these coefficients depends on the coefficients of the second fundamental form. Here, for us, the inflection points has rank 2, and at all these points, we have that all the directions are solutions. Then all the directions are asymptotic directions. And the conic point is a rank 3 point that we are not considered here, but all the directions are also solution of the equation. Just to compare, in the cases for surfaces in R3 and R4, the equation of the asymptotic directions are quadratic forms in the U1, the U2. Then we have at most 2 asymptotic directions. And for surfaces in R5, it is a quintic form. Then you have at most 5 asymptotic directions. And also the coefficient depends on the coefficients of the second fundamental form, the first case, and the second case also on their derivatives. Here we have the coefficients of this equation that are given by the cofactors of the matrix of the second fundamental form. Okay. Then, we study the geometry of the surface FAD minus 1 of 0. And why we did this? Because here we are thinking the Davidov's method. When here I have the plane UV, and we lift the surface. For each point here, UV, we have P1, P2, that represents 2 asymptotic directions upstairs. And in some points, Well, we can have at most 4 in your case. In some points, we can have 1 like this. If you, let me just put some color here. This line, we project here. Then when we are here, we have only 1 P in the elliptic surface. Then, at the first, we thought that this elliptic surface was a isolated, is a surface with isolated singularity, but we prove that we have a line, a curve of singularity upstairs. Then we are thinking that we have a projection of the surface to the plane UV. This project gives 4 asymptotic directions in the plane. The projection of the discriminant FAD equal to 0 is given by the curves d alpha equal to 0 and the M2. The curve M2 is the image of by the projection of the singular set of the surface FAD equal to 0. Then here is the line, is this one. This is M2. The blue one. And the curve d alpha equal to 0 is the discriminant of the projection. That is the singular points of the projections. That means this part here. This one we call d alpha equal to 0. When the rank of alpha is equal to 0, then this we prove also that FAD equal to 0 is written by a complete square. Then we have at most 2 asymptotic directions at the points where the rank of the second fundamental form, the matrix of the second fundamental form is 2. If we consider the 3 by 3 max of the second fundamental form, and we call by my the points where the rank of alpha is I, we have the following. Given a surface M, there exists a residual set of the embeddings such that for any embedding in this residual set, we have M equals to M2 union with M3, where M3 is an open subset of M and M2 is a smooth curve on M. Oh, sorry. We prove also if the point is belongs to the M3 region, then generically the surface FAD equal to 0 is smooth at this point. So if F minus 1 of 0 is singular at this point, then the point has rank 2. Because of this, we need to study the rank 2 case. We prove that generically the singular sets of this surface is a regular curve. Then it's not isolated. And for a generic embedding of a surface, at a non-inflection point, a singularity of this surface is A infinity or a cross cap S0. At an inflection point, a singularity can be A infinity, a cross cap, or S1. The normal forms of these singularities are here. And here I just would like to comment that xy represents our uv, and z represents p for us. Then we did some diffeomorphism here, but we preserve the p because we want to preserve the number of the asymptotic directions in our case. In accordance with the normal forms that we get before, we have then 3 parameters, at most 3 parameters. And if you remember, we call the normal forms by M2 hyperbolic, A elliptic, M2 hyperbolic, A hyperbolic, and in which case we study then the number of asymptotic directions in accord with the parameters, and also the lifted surface. But we have 2 situations. We have 2 charts, and we have 2 lifted surfaces at each point. If the UI is different from 0, then here we have 2 lifted surfaces in each case for each point. In this situation, we have the lifted surface like A infinity for both, but instead to have 2 asymptotic directions, you have nothing because of this phenomenon here that we call ghost phenomenon, because that I will explain now. The ghost, when we have a ghost phenomenon, in which case you will not have 2 asymptotic directions here. For example, ghost and ghost, no asymptotic direction. Ghost in this one, we have just 1 lift P that represents asymptotic direction, but it is on the cross cap. Okay? And here we have 1 point of this charge and 1 point of this charge. Then we have 2 asymptotic directions upstairs. Well, to know that it's not, there is no asymptotic direction, in fact, here, we need to study the binormal direction. Then we need to be attention in these cases here to see that there is a solution of this equation that could be asymptotic direction, but we need to check in some special cases, some special points, because there is no binormal direction associated. And at each asymptotic direction, we need to have a binormal direction associated. Otherwise, it will be not an asymptotic direction. Then for this case, we have a missing point at the lifting surface upstairs. Okay? Then we study all the cases. For example, here we have inflection points, and it also appears. In some cases, this upstairs only have 1 asymptotic direction or inflection point because of the position of these pictures. If you have A infinity here, then this is the plane, UV. If this one is an inflection point, then you have here that all the P are solutions because all the asymptotic direction are solution. But in the other case, we have the same picture upstairs. But for this point that is not an inflection, I have only one solution here. Because of this, you also need to take care of the position of the lifting surface. And we preserve the variable P to not have some confusion about this. Upstairs, you have the same one, but different kinds of solution for the AD directions. Well, some examples here that we realize in these cases. We give you a parameterization of a spacelike surface that is given by x equal to 1, because this is in the 5 de Sitter space. Then we consider f, g, and h given by this. And then this part is a roof because of x is equal to 1. The first jet of the matrix alpha UV is given by this. And to simplify the notation, we are using A, Y, B, I, C, I. And the examples below realize different singularities of the 4-web given by FAD equal to 0. The yellow curve is the M2 curve. That is the singular part of the projection of the singular part of the surface. And the gray curve is the D alpha equal to 0. That is the singular points of the projections. At the case alpha hyperbolic case E of our normal forms, we consider this situation. Then FAD equal to 0 in the chart has a closed cap singularity or A infinity ghost. Then you have two lifting surface. Only one point here represents a asymptotic direction. This point here is not, because there is no associated binormal direction, then you call ghost. And when you project this, it's like this. Yes, you can project this line and this line go to the yellow line. And P1 and P2 here is represented in this region because there is two asymptotic direction when we project. Nothing in this part when we project. For the order normal form, alpha H P, hyperbolic, parabolic case, if aparabolic. Then we have the lifting surface, the two charts. This will be A infinite, and this one will be cross cap. Then we have, when you project this line and this line, you will be the yellow line here in the projection. In this part, we have a P1 and P2 asymptotic direction, and we project, and P1 and P2 here also. Then we can project in this green part that it has 4 asymptotic directions. This line is the singular points of the projections. That is the gray line here. And nothing asymptotic direction here, but here it continues to have 2 asymptotic directions in the projection. This situation is a little bit more complicated, but well, I will show the global picture here, because we have local pictures for both charts. These are the cross cap, and when you project the cross cap, we have a region with 4 asymptotic directions. Then, if we see here, we can see that is this region. You project P1, P2, P3, and P4. You got 4 asymptotic directions. In this part here, we have only 2, and in this part here, when we project, we have only 2 also. Here, nothing. That represents this part, and so on. And it's a little bit more complicated, but the surfaces, the lifting surfaces project the number of asymptotic directions. Well, we also want to study the configuration of the asymptotic directions, the curves of asymptotic directions, but first of all, we are studying the surfaces given by the binormal directions that has another equation, and we want to see if there is some relation with or duality with these surfaces that we got for the asymptotic directions. Thank you very much.